Hi guys, in this video I'll demonstrate the technique of distillation and the distillation setup. We'll also briefly discuss some of the theory behind distillation. The first step in the distillation setup is to start with our round bottom flask, which we will distill from. We need to go ahead and put our unknown sample into the flask. I'm not going to do that for the purpose of this demo. Need to get it into the flask with some type of funnel. At that point we need to add a stir bar. Anytime we're heating we need to stir. And then we need to clamp our flask securely. The flask is clamped right at the neck. Once you get it clamped, then this can be moved or adjusted later on. Okay. The idea of a distillation is we have a liquid, or typically a mixture of liquids, and these are going to be separated by the distillation technique. The idea behind the separation is hopefully one liquid will boil at a higher temperature than the other, and so there's a difference in boiling points. The lower boiling liquid, we can get it to boil out or distill out of the flask first, and then we will have to recondense that, and then we'll come this way in our setup and we will collect that lower boiling compound in some type of container, and that will be separated. And in the ideal case, the higher boiling compound will remain behind until we turn the heat up, and then we can get that compound to distill over and collect it in a separate flask. That's a very ideal situation though. But let's continue with the setup. We have our compound, our unknown liquid in the flask. We're going to have to heat this and stir. Stirring is done with your stir plate, which is in your hood. That's of course plugged in. We're going to heat using what's called a heating mantle. The flask can be sort of submerged down into that mantle there. This is not plugged in directly to the outlet. Instead, it's plugged into a voltage regulator or rheostat. If you plug this directly into the mantle, it's going to be on super hot and you won't be able to control it. This allows us to control the voltage and thus the heat output. So that's plugged in, and then we can control that here. This is going to sit on top of your stir plate. We are not heating with the stir plate. Do not turn that on. If you turn that on and you heat this, you're going to ruin this unit. This is just stir. One other thing that's important here. Very often you like to have this raised up eventually in the setup. Okay, we'll mention why. That can be raised with a lab jack to actually jack it up. Those are quite expensive. In the teaching labs here we usually use blocks. Wooden blocks, they're found usually around on top of the hoods. These can be something like this. And you can raise that up. Once you get it raised up, this can be lowered down, and you just want to barely touch the bottom there, get it nice and level, and then tighten that up. Okay? Please always make sure your clamps are very tight. I see a lot of setups where these are not tight and everything is just sort of loosely held together. It's not good. Okay. Now ultimately we may not be able to do this. We may only be able to raise this up one block level. What we will see, especially in the hoods, is when we get too high and ultimately we start adding our thermometer, about here, the thermometer could hit the top of your hood. Some thermometers are longer than the others, and so that could be a limiting factor for raising this up. Why do we want to raise this up? Because once we get everything together, it's going to be built, it's going to be very difficult to move this. And so if you want to remove the heat, well, you can't just turn the heat off. This will remain hot for 10-15 minutes. So if you want to quickly get this away from the heat, instead of raising this up, which is difficult, what you can do is you can pull your blocks out and you can just let that go down. So now it's not heating. nearly as much. Okay, I'm going to add one block back. Actually, one block is sufficient just to give you enough room there to lower that down. Get this lowered here. Now, typically we do heat with a heating mantle. Occasionally I may give you the okay to heat directly on your hot plate. Some instructors may not recommend that, but we may do that, and that's okay for me. Okay, we have our liquid, flask, stir bar. The next piece we want to put here is, really it depends. If you're doing a simple distillation, the next piece you'll put there is your three-way adapter, and that goes here. I'll turn this just a little bit. Maybe that's obstructing the view. Three-way adapter. Now we're doing glass joints here. Okay, very important. Anytime you have a glass joint, you want to put a little bit of grease on it. There's vacuum grease around. Put just a little dab of grease. You get your paper towel. I usually just use my fingers and then kind of smear it around right at the top of the joint. And then you put what you want is this to twist without really catching. It's still sort of catching there. Do a little bit more. You just need to be careful and not use too much grease, or you'll end up with grease everywhere, and grease will get down into your product or your distillate, etc. Now that's twisting sort of nicely. And it's a good seal. Okay. But for us, we're going to be doing what's called a fractional distillation. We'll mention why. Fractional distillation requires that you use some type of fractionating column to increase the distance of the distillation path. Now, this is a standard fractionating column, but it's quite long. And if we put this here, we're going to end up with a setup that's quite high, and then we're going to have the thermometer problem. Instead, we're going to use a drying tube as a fractionating column. It's shorter, but it is called a drying tube. That's okay. What we're going to do is we're going to stick our fractionating column in here. That's nice. Then we're going to put our three-way adapter on top of that. We've extended the length. On top of our three-way adapter goes our thermometer adapter. The thermometer adapter is this two-piece glass with a rubber adapter piece there, and your thermometer slides in. You want to kind of twist as this goes in. You don't want to snap this off. Hopefully it'll just slide in smoothly. Okay, where do we place it at? Okay, that's important. This goes here. Got a glass adapter. Of course, a little bit more grease there. And it's a nice seal. Important here is, where do we actually place the thermometer bulb? Okay, you see that can go up or down. The thermometer bulb needs to be just below where this takes a right turn and goes towards the condenser. Because the idea is your liquid is going to be vaporizing, vapors rise in here. They hit the thermometer just about the time, at the same time they take a turn, and they just condense in your condenser and then come out, and you collect it. And we, of course, once it starts condensing, the temperature drops. We want to measure the temperature of the vapor right here, where ultimately we're going to collect it. Issue here, sometimes students have this too high. The vapor can sort of just take a turn and never really coat the thermometer bulb, and your reading will be too low. The other is, if the thermometer is too low, This temperature can be higher because this still may be a mixture here. And it's not an accurate temperature of what's really coming over. So there is a correct placement. Now these thermometers do typically read a little low, so I will sometimes encourage you to push it sort of further down than typical. There are glassware setups that do have an exact placement. This here, it's sort of a separate adapter. It's just a joint. This thermometer has a joint, and when you put it in, there's no variation. And so this manufacturer built this to have the bulb at a certain place, and that's it. But this type of glassware is much more expensive and typically not used in the sophomore organic teaching labs. Okay, so we got this here. Now note, I'm not going to put a clamp anywhere else. The clamp goes on your round bottom. I see students sometimes clamp here and not even have a clamp there. Very bad. Clamp the round bottom, everything else will assemble here, and we're fine. Okay, vapors come up. We've increased the path length. That helps the different vapors separate. We'll talk a little bit more about that. And you get better fractionating of your sample. Here we're going to put our condenser. You have condensers in your hood. They're already hooked up with water. This is a water-cooled condenser. Water goes in at the bottom and out at the top. That's the way it should be set up. Of course, that's the bottom if it's vertical. If it's horizontal, it's the same. It's the lower portion here with this lower joint. This is going to go here, need a little grease. Okay. Now, what holds this here? Because this is horizontal here. This can fall off. Now, you can get clamps to put here. Also with the hoses here, the hoses will be pulling this a little bit and make it want to come off. You have to secure this. In the lab here, we will secure these with rubber bands. Okay? Put a rubber band over here, and then you can stretch this sort of like this. Alright? That'll sort of hold it. The problem is you're not going to be able to do what I just did because there's going to be a hose here. So you're not going to be able to slip this on. Instead, what you can do is sort of wrap this around the hose, sort of like this, and then you can put this over another piece. But there's a variety of ways to secure that with rubber bands. We do need to secure it. I'm just going to secure mine by just slipping it over that there. Okay? Do need to make sure this is tight. Okay. Vapors rise up. They separate during the process. Extended path length. Hit the thermometer. They give a temperature reading. The vapors have to turn right. There's nowhere else to go. They start coming through the water-cooled condenser. They condense back to liquids, and then you will have liquid falling out here. At this point, we will collect the liquid. Variety of ways to do this. You should have vials, clean vials to collect. We can hold this here. Variety of ways to hold that because putting it here is sort of a risky endeavor. Letting it drop that far. There are, your ring stand could be used. It's in your hood as a platform. You could put something like this, and there you go. You now have a platform and you can drip directly into a vial. As you go along, we will be trading out vials and collecting different fractions which will have different boiling points. By the way, each fraction you need to number with your Sharpie and indicate the boiling point range of that particular fraction. Then you cap it up and you set it aside. While we're here, let me show you some other possibilities for this. A curved adapter is a very common piece that you would add on the end here. You would need to secure that. It's got some grease already on it. You can secure that with a rubber band. Sort of like this. First off, that extends the path length. So for example, if you can't make this work for some reason, you can do this. And now you have an extended path here that the liquid will come down into your vial. But this piece is not needed if you can get this up high. When is this piece needed? It's particularly needed if you're doing a vacuum distillation. We won't do that in Organic 1, but we may do a vacuum distillation in Organic 2. When you do a vacuum distillation, everything is under vacuum. You hook a vacuum hose up right here, this barb here, for a vacuum. And everything has to be closed. Because everything has to be closed, you can't have an opening here for liquid to drop into a vial. Instead, you connect a vial directly to that joint. This is going to have to be supported somehow so it won't fall off. Although if we're under vacuum, that's not going to fall off very easily. Now everything is closed. We can pull a vacuum. Everything's under vacuum. The only problem with this is if you want to change and collect different fractions, you'd have to break your vacuum. You have to break the vacuum and change it out. Just to show you this, there are other glassware available. What we have here is a very nice piece here. We can put this here. This is going to have to be supported somehow. At this point, you might want another clamp here. This is getting kind of heavy. Let's add another clamp and illustrate that. Sort of put this here. That's sort of blocking that. In your hood, you have these clamp supports all in the back there. I'll set this here. You can sort of support this here and just tighten this so it's just putting a little bit of support on there so it's not, so you won't pull down with any weight. What I would not do is tighten this tight. If you tighten this tight, it's going to start pulling on that. It may pull that out of that joint. It may put too much torque over here. So just a little support just so it doesn't push down. Now this is supported. This piece, which is called a cowl, going to have a clamp. You can rotate this and you can collect 4 fractions without ever breaking your vacuum there. So that's a nice piece. Just wanted to show you that. So let's get rid of the curved adapter. Go back to the setup here. Do something like this. Something like that. So something like this is going to be sufficient for the distillation of your unknown in this week's lab. Okay. So this is our setup for distillation. Once we're ready to begin, you do need to get the TA to check or get me to check your setup, make sure everything's good. All your joints are sealed, there's no gaps. We'll then get it heating. This is plugged in. Turn it on here. Just get this turned on. This has numbers 15 to 70. Those numbers do not mean temperature. That's just voltage. Higher number is going to be higher heating. We also want to get our stirring on. Remember, we're not heating with this hot plate. We're just using this for stirring. So we can get our stirring on. Begin the heating process. We want to heat this high enough to make this boil. Everything is done by observation. Okay. Let's go through the boiling process here. Heat this up. We start getting some vapor form. We'll see the vapor here. The vapor will eventually start rising up through here. Also, different students have different boiling points. Some unknowns may boil at about 70 to 80. Some may boil up into 150. Obviously, the ones that boil up 150 are going to require much more heat to get them to vaporize and distill over. Although everybody does have a low boiling impurity that boils below 50 degrees, and that's what we hope to get to boil over first. So, we get vapor coming up. You can see it here. Eventually that vapor is going to hit the thermometer. At that point, we're going to read the thermometer. And I can say a note about that. This orange adapter here will block a low temperature reading. That's okay. The lowest unknown is about 60 to 70. That's clearly red. If something's coming over where it's blocked, you know that is below 50 and it's not your unknown. Now, you're not going to be able to record a precise temperature. That's okay. Just say that the temperature could not be read because of the thermometer adapter. Once we have vapor turning right, it will be condensed in the water-cooled condenser. By the way, this has a slow trickle of water running through it. It's a spigot. We turn this on very gently. The water will come through. There's an outlet line into a sink near your hood. You want to check that outlet line for a slow trickle. If this is a fast stream of water, we're going to risk popping hoses off the joints, and that will routinely happen because students turn the water on too high. As long as it's moving through the system and you see the water coming out the end hose, that is sufficient. So the vapor hits the condenser, water-cooled condenser, vapor condenses to liquid, it rolls downhill into your flask and we can collect that. Okay, let's talk about separating fractions. What if we had two compounds? Now, a mixture could be multiple. Well, let's discuss as if we have two. I drew these on the board here. Let's sort of look at the theory behind an ideal distillation separation. Let's say we have two compounds in here, 5 milliliters each. The boiling point of the compounds, one is 50 degrees and the other one is 100 degrees. See. So if we had this scenario, 50-degree difference in our two liquids, these should be separated pretty easily. This one's going to boil first. Hopefully this one will come over. And then we'll have to turn the heat up to get the next one to come over, and we can collect that in a different vial. Let's sort of graph what that may look like. I have a graph here with temperature and volume in milliliters. Okay, we have 10 milliliters total. Something like this is essentially what you will be observing or you want to be considering. Let's say we start heating it up. What's going to happen? Vapor will rise up. hit the thermometer and start coming over. In the ideal case, as soon as something hits the thermometer here, it'll read 50 degrees. And as soon as a drop starts coming over, the temperature will read 50 degrees. So as soon as we start getting volume, the temperature will be 50 degrees. And in the ideal case, since we have 5 milliliters of that component, it'll stay at 50 degrees until we collect 5 milliliters. And the thermometer always reads 50. At that point, that one has come over here. What will happen next? Well, if this is only heating enough to distill 50, the other compound will not distill until we turn up the heat. We turn up the heat sufficiently, then this one will come up and hit the thermometer. And because it's only the high boiling compound, that should read 100. And at that point it starts coming over. So we may have a gap between the two. We change out our valve. We now have the second compound coming over. As soon as it starts coming over, the thermometer reads 100. And we collect another 5 milliliters. And from here to here, the thermometer may actually drop, because if this is clean separation, nothing's hit the thermometer, it may drop, but all of a sudden when the second vapor hits, that'll rise quickly to 100. Without collecting any volume, it'll rise quickly to 100, and then we'll collect the other 5 milliliters. Okay? So this here is sort of the ideal case, but it's really almost fantasy. Your separation will not be this clean, and it will take more vials, and it'll be more tedious than that. Instead, your separation of these two will probably look more like this. You'll probably get some liquid coming over with a boiling point maybe about 30. And instead of it being constant, it may just be gradually rising. And what you're doing here is you're collecting here. Now we've collected maybe 1 milliliter. But the boiling point was never constant. Hopefully what will happen is it will kind of go up and it'll sort of become constant. Your goal is to collect a constant boiling fraction. So it starts rising. Once it becomes constant, you change the valve. So this is valve 1 with a boiling point of 35 to 50. Now we're collecting valve 2, and the boiling point is pretty constant, but then it starts rising. Once it starts rising, we change the valve. We record this boiling point as maybe 50 to 51. This starts rising. It looks like it's settling out. Maybe you change the valve here. You record that range. Then it starts rising up. Maybe it'll shoot up high, and then maybe it'll do that. Valve here, here. So this is valve number 4, that's valve number 5, that's 6. That's almost too many. Theoretically, you could use as many valves as possible. The problem is we have a limited number of valves, and 6 should be sufficient. 4 or 5 should be sufficient for this. So what we have here is valve 2 was pretty constant. Valve 6 basically was 99 to 100 maybe. The other valves really didn't contain a constant boiling fraction. I say constant, basically looking for a tight boiling point range. Something like this. Ultimately, you want one good fraction. This would be your unknown, and this would be your recording boiling point. And the tight boiling point range is an indicator of purity. A pure compound will boil at a fairly constant boiling point. where a mixture will not. What's going on here? Why is this kind of rising like this? This is probably a mixture of the low boiler and the high boiler. Because it's a mixture, it sort of has a boiling point in between, and it doesn't really stay constant. Why do we get mixtures? Why do they not separate cleanly like this? Well, this is overly ideal, because as the low boiler is boiling, it's not reasonable to expect that the other compound is just sitting there doing nothing. The other compound is going to have some type of vapor pressure, and some of that compound is coming too. Even if the boiling point is 100, there's going to be some vapor pressure here of the higher boiling compound. That's analogous to water here in the air. The boiling point of water is 100 degrees. Does that mean there's no water in this air at 22 degrees? Yeah, there's water vapor, there's humidity in the air. Now, the tighter your ranges are, your low boiler here, your high boiler behind it, that's the importance of the fractionating column. If we can increase the length that the vapors have to travel, this gives them more of a chance to separate. It's like two runners running a race. If me and another student want to run a race, if we ran into that wall, 10 yards ahead, 15 yards ahead, we'd probably get there at the same time. But if we ran to Walton Way, 100, 200, 300 yards, etc., then one of us will probably get there clearly ahead of the other. So if we can extend the path length, more of a chance of separating our fractions. Okay, so for the unknown distillation, the goal is to ultimately collect a fraction that has a tight or narrow boiling point range. The one variable here is, what you'll encounter is, when do I change the valve? Okay, you change the valve. It looks like it's maybe constant, but it starts going up and up and up. So this is no longer constant. So you change the valve again. Then it's at some point it will become constant, hopefully. And that will be your constant fraction. Okay. I don't know that there's anything else to say for this distillation setup. Round bottom, fractionating column, Threeway adapter, thermometer adapter, condenser, water-cooled condenser, slow trickle of water, collecting here. Important here is, when you're doing a distillation, don't let it go completely to dryness. If it goes completely dry, then the temperature will typically rise very quickly, because nothing's maintaining the temperature. And basically you'll start getting to the temperature of glass. And at that point, with vapor still around, maybe in here, that just could lead to a fire hazard. Okay. I think that covers the distillation. If there's any questions, of course, we can address those at the beginning of lab. You will be doing distillations again in Organic 1, and you will also do distillations in Organic 2. As I mentioned, there is a lab in Organic 2 of mine that we do a vacuum distillation. The curved adapter, we'll put a vacuum hose here. The purpose of the vacuum distillation is if you have a very high boiling compound, maybe it boils at 300 degrees. If you distill it under vacuum, that boiling point will be reduced down to maybe 150, something more manageable. You don't have to get quite as hot here. Also, the compound may decompose at its boiling point. Okay guys, good luck with your distillation. Good luck with getting a tight boiling fraction of your unknown liquid. Once we get the unknown liquid, then you're off to collecting data such as IR, refractive index. You can do the optional density determination, etc.